You know what graphing really needs? Another freaking axis. That's right, ladies and gentlemen, we're going into 3 dimensions now. We're in the real world. No more of this mamby-pamby, just X and Y and the little curve sprawling away across. No, we're making space. By the way, I'm using James Stewart's Essential Calculus 2nd edition. If by chance you want to follow along, why you would, I have no idea. So when I say 3D space is new, I mean I'm kind of lying. Last semester, if you took Calculus 2, it's most likely that you were introduced to finding volumes by revolving something around an axis, you know, shell method, disk method, washer method, all that kind of stuff. But that wasn't really 3D space. I mean, we were given a cross-section to rotate, which was in 2D space, and we were given an integral and just told to solve it. It never really emphasized the 3D space. It more emphasized the integrals themselves. But that is all about to change, so it is definitely worth reviewing how to set up 3D coordinate systems. Definitely worth it. So that's something that I'm going to be doing. Somebody left their marker here. Ooh, it's permanent. Oh dear. I even brought my own dry erase markers, but I just saw that someone had left a marker here, and I'm like, oh my goodness gracious, I'm just gonna use someone else's marker, not waste my own ink. This is what happens when you cut corners. Oh my god, this is why USC's tuition is so expensive. Idiots like me keep ruining the whiteboards. How to get permanent marker off of a whiteboard. Alright, internet, you better not be lying to me. Oh my god, it worked. I had no idea that was a thing. So, normal coordinate systems, we know. We have 2 axes, you know, X and Y. Pardon my handwriting. There's nothing you can do about it. We're obviously not flat. So what we gotta do is we gotta add a 3rd axis. Now you might be thinking, how the heck do we know that our 3rd axis is the same? Well, I'm glad you asked, because it turns out that some smart mathematicians thought of this. It's called the right-hand rule. And it works like this. Basically, you take your right arm and you put it along the y-axis, and you curl your fingers so that your fingers line up along the x-axis, and whichever direction your thumb is pointing is the direction that your z-axis goes in. For example, if I were to do it like this, I would put my right arm I'm erasing this to make it easier for me. This should allow my body to bend in a way that it's supposed to. So like I said before, you need to put your right arm along the y-axis. I should be over there. So you need to put your right arm along the y-axis and then bend your fingers so that your thumb sticks in the direction of the x-axis. So as we can see here, the x-axis in this particular coordinate system is pointing into the whiteboard. I don't think this holds any mathematical significance or consequence. I think it's just a way for mathematicians to basically say, hey, we're all on the same page here about how our axes look. Let's move on to some actual math. We got point A and B here. They are friends, but the sad thing is they live far apart from each other. So the 3D distance formula is literally just the 2D distance formula with z2 minus z1 squared tacked on the end. Yeah. So statics basically just deals with objects that are experiencing a constant velocity. So it doesn't need to have zero velocity, it just needs to be zero acceleration. Which makes sense, because if you have zero acceleration, that means that the net force being applied to an object is also zero. So obviously we can't start anywhere except with vectors. Vectors, of course, are...
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
Vectors are particularly useful because they can describe quantities with direction. We use them, for example, to show quantities such as displacements, velocities, and acceleration. Scalars, on the other hand, are parameters that are used to describe quantities that have no direction. Here's our little force vector. It's looking very cute tonight. Now, force is characterized by four main things. 1 is the point of application, 2 is the magnitude, 3 is the line of action, and 4 is the sense. A resultant force is what happens when you put two forces together. It is the resulting force vector. So as we can see here, we have two vectors, force 1 and force 2, being added together to produce this new diagonal vector, force sub r. As we can see here, we have two forces being applied at point A, force 1 and force 2, that are being added together to produce force r. The resulting magnitude of the final force vector is given by this equation, which is derived, of course, from the Pythagorean theorem. Because look, right triangles. Snuck up on you. So not all systems of force equations are as simple as this. I mean, let's be completely honest, this is just a glorified 2D axis system. For example, we could have something that looks like this. Now, I know that this system of force vectors looks particularly intimidating, especially because there are no right angles. But smarter people than I have actually figured out how to find these force vectors pretty simply, and here's how to do it. We use something called the parallelogram law, and here's how it works. You take one of your force vectors, let's say P, and you go out to the end of the force vector, and then you take a look at Q, and from the end of P, you draw a dotted line that is parallel to Q. So we're just going to guesstimate this right here. This looks like that. Yeah. So then you go down to Q and you do the same thing that you did for P to Q. So you go out to the end of Q and you take a dotted line that is parallel to P and you go like this. And notice how, this makes a parallelogram. Now, where these two dotted lines intersect, where they cross, at that point from A is going to be where your resultant force vector ends. Let's call this resultant force vector, Steve. So, Steve ends where the two dotted lines intersect. It's as simple as that. I'm sorry, Steve, you have to go. So we have P and Q, the force vectors again, except this time we've lined them up tip to tail. So now, to add these two vectors together, here's what we're going to do. Any questions? So we've gotten a new vector here, P plus Q. Triangle rule. Pretty, appropriately named if you ask me. So if you didn't know, vectors can also be decomposed into separate x and y parts. Say we have a vector going from the origin 0, 0 to 1, 1. The x component of this vector would be, of course, 1, and the y component of the vector would also be 1. So we can draw two vectors, one here, this is the x vector, and one here, this is the y vector. Simple. But of course, if you're just given a magnitude and say an angle from an axis or some other reference point, you're not going to be given coordinates and you're not going to be able to directly see what the x and y components of the vector are. But have no fear, there are equations for this. So if you want to decompose an unknown vector when you're just given a magnitude and an angle, these are the equations that you're going to use. F of x is equal to f cosine theta and f of y is equal to f sine theta. Now, there are two important trig laws that I was introduced today that I want to go over. It basically states that there's a certain proportionality between the angles of a triangle and the sides that are opposite to them. So if you notice that angle A down here is opposite to side A, and angle C is opposite to side C, and angle B is opposite to side B. Since we know that all this stuff is proportional, we can say that sine of the angle A over A is equal to sine of the angle B over B is equal to sine of the angle C over C. Now this is really important because it allows us to find values in systems of vectors that we don't know. For example, if we're given some angles and some sides, but we're not given all of them, we can use the law of sines to find the missing values. Now, the law of cosines follows the same situation as the law of sines, where the corresponding angles and sides are opposite each other, except instead of just having one simple, pretty, beautiful equation, we have three of these monsters. Now, a good thing to remember is the law of sines is generally used when you want to find an angle. For example, you have two sides and an already existing angle, then you can use proportionality and inverse trig functions to just solve for the angle inside the sine. But the law of cosines is more used to find a side. It's more convenient that way because it's already set up for that. So, with all that out of the way, let's do an example, shall we? So we have two different forces being applied here at point A, and we want to find the resultant force, the magnitude, and the angle. Now, we could use the parallelogram law of parallelograms? Parallelogram law? Parallelogram law! We could use the parallelogram law to estimate the resultant vector of these two forces, but we don't want an estimate. We won't stand for that. Let's use some of the laws and rules that we have learned in the past day to solve this. This is the setup for the law of cosines from our base equations. This is the equation with all the numbers plugged in. This is what r squared is equal to. And now if we just take the square root of both sides, we will get the final magnitude for the vector r. Now we need to use the law of sines to find the actual angle. This is the law of sines equation that's derived from our law of sines base equations. Now, there are a couple important things to note here. I neglected information, don't be me. When I was first doing this problem, I made a mistake. I thought that sine of angle A, I thought angle A was this 20 degrees over here. It isn't, and here's why. The law of sines only works because we're dealing with known angles, well, angles with known relationships that are inside of a triangle. So the angle A is actually this angle that's inside here, and the angle B is this 155 degrees, which we got by using the law, wait, how did we get that? Hold, please. Oh, wait, I didn't notice that. Okay, so notice how, basically, if we just continue along this line, it's like, it's a straight line. And as we all know, a straight line is just 180 degrees. And since this is 25 degrees off of this straight line, we just subtracted 25 from 180, and that's what got us this angle of 155. Going back to the law of sines, we are trying to find angle A. We are not given angle A. Angle A is not 20. That is something that I did wrong. So, let's plug some numbers in. I'm hoping y'all can't hear the people that are next door. They're being very loud. Anyway, this is the equation with the numbers plugged in. Now, using algebra and inverse trig functions, we get the answer that A is equal to 35.04 degrees. So now, from all this calculation, we know that the magnitude and angle of the resulting force vector of the force vectors P and Q are 97.7 newtons and 35.04 degrees, respectively. Statics is done. We move on to the doozy. Now, Physics 152 here at USC, Physics 2 generically, has a lot to do with fields and electromagnetism. And we got an intro to that today, very basic stuff. You know, electrons are negatively charged, opposite charges attract, similar charges repulse, that kind of stuff. So the thing from physics today that I really want to get down tonight is Coulomb's law. Coulomb's law is a force... Quiet, please. Coulomb's law is a force equation that describes the force exerted on two objects that are charged. An important thing to start out on is that the direction that the force is applied in depends on the charge of the particles. So, if you have two particles of the same charge, the force is going to be pulling those particles away from each other. But if you have two particles of the opposite charge, the force is going to be drawing the particles together. Capiche? So this is the equation for Coulomb's law. It is force is equal to the first charge times the second charge divided by the distance between the two squared, all multiplied, times Coulomb's constant. And Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Now, I don't know about you guys, but I don't want to have to memorize that, so that is going on the cheat sheet. So this is the situation that we have. We have one particle that is positively charged with a positive charge of big Q, and we have another particle that is positively charged small q, and they are a distance of r. So plugging these parameters into Coulomb's law, we get this equation. Obviously, your results may vary because not every two particles have this exact distance and these exact charges. You can plug real numbers into this equation. It works. I'm just not doing that because I just want to make sure I understand. The reason that this equation works is as such, because the stronger charged you have your particles, the more force is going to be exerted in between the two. And much like gravity, the greater the distance you have between your particles, the smaller the force will be. So your force is proportional to the product of the charges and inversely proportional to the distance squared. Also, make sure that if you have a negative charge, that you take the absolute value of it before you put it in your equation, because we're really looking for the magnitude of the force. This equation won't tell you which direction the force is being exerted in. It's just going to tell you what the force is. The way you get the direction is by looking at the charges and imagining how they would interact with each other. My public policy class hasn't even started yet.